So what I'm going to do today is I will, let's see, let me move this stuff around. Maybe start a new Suno here. So I think that we have a lot to talk about. So so I'll see like how far we go today. So I may talk a little bit like recurrent neural network, and I don't think we'll spend as much time as we did like in the past because there are more interesting topics now than RNN. And so, but before that, like I like to spend some time to talk about like self-supervised learning. So I don't really have slides here, but like I have like just a copy some. Oh, by the way, like there's a very good course, like online course by Yana Kun, like on new NYU, and you can easily find it like if you Google it. And there's a lecture like I guess yeah, one lecture on self-supervised learning. Yeah, also is a very nice lecture. If you, I basically just borrow most materials from that lecture. So first of all, like I guess we uh let's like explain like the motivation and what is self-supervised learning. So the idea is like you know that like we have what should I say, like for all the success of like deep learning or neural network at this moment, like it's mostly focused on like supervised learning. Right at the beginning, probably I won't cover that. Like right at the beginning, there's something known as like using unsupervised learning to do like initialization of weight, and that's like I guess it's around the time of like 2007 and 2006, and that's the time like they did some useful application using like unsupervised learning. But like for recently, like for recent decade, I guess mostly the success is on like supervised learning. And that's good, like that's great, that's okay, like using supervised learning. But the problem is like whenever we use supervised learning, we need to have label data, right? So but label data is typically very expensive to collect. So that's why like people think of like can we get away with that, like trying to um, just like do unsupervised learning, right? In the sense that we don't have label, but we kind of like um, leverage some technique in like supervised learning and just train it like train a model even though we don't have a label. So it sounds magical at first, but the idea is pretty simple. So the idea is that like we want to look at like whether we can find a way to generate some label like for free. So let's say we have as I mentioned, one really simple example is a language model. For example, if you think of like just doing a kind of training a language model using like data on the Wikipedia, let's say, of course the data on Wikipedia is not labeled. Eh? We cannot use that to train, let's say, a translator immediately. I say I cannot use that to translate uh, English to Spanish. Maybe I can. Maybe I can just find pages that have like have English page and also Spanish page and try to find. But still, like we need to find correspondence for that. Like if we do that, apparently you have the English page can be very different from the Spanish page most of the time. So but what we can do is like we can just take like all English tests like on the web and just like consider that as some kind of like label data by assuming that like we by constructing a model that's not going to do translation directly, but just a model to do prediction. So a model that we are going to predict the next character. Let's say I have this just this phrase here. Let's say like I have kind of like self-supervised. I do a character model here. So for the E here, like I'm trying to look at like what I had in the past and predict the next character D here, let's say. And this this apparently will be like some kind of label data, right? And I just I can train using any kind of like supervised learning, or like I can just think of like any supervised learning model can be used for this kind of data. And then after I have a this kind of language model, I can use that as an intermediate model and generate some features, and then features maybe later on like do a simple classifier or even SVM to for like additional applications. So and then if you look at that like what we if you think about like what we just talked about, uh we can like kind of classify like uh the task, the possible task into two different one. So one is like we call it this p-test task. So in this case, this language model here.
Dr. Chang,
Yes.
sorry to interrupt. Are you sharing the slides right now?
Oh, I'm so sorry about
It's
that.
okay. I just didn't know. Thank you.
I'm not really okay. Okay. But I don't. Luckily, I don't think you guys miss a lot. So it just say that I didn't really write much. Right? For let's say like what I'm saying like okay, we have this simple language model or like character model that given like previous whatever phase that we have input so far, it will be our input, and then we're trying to predict the next character. And we can consider this kind of language model like uh, as some kind of like people call it like pretext task. And then later on, let's say you have like some downstream, people call it downstream task, uh, can be maybe doing translation. So let's say like I will use this as some form like to pre-train the model a little bit, use the p-test task to pre-train a model, and then I may patch the model like with additional layer and trying to tackle the downstream task. So this is like the uh, key idea of the self-supervised learning. And I will just give like a couple example here. So I borrow from let me so or maybe I will just drag this one. Oh, where is it? It just disappeared. Mm. Oh, that's very weird. Did I close that? Mm. This is really weird. Um, oh, I don't know why. Just suddenly close. So now this is one example here. Uh, a one example of p-test task for kind of image or computer vision application. So I can have a p-test task is just doing this. I trying to predict like I have an input like just like a patch. Let's say I take a patch, right, random patch, and then partition into like line segments here, line patches here, and then I will randomly like pick one of these segment like out of this patch here, and then from the given the center patch here, we are trying to predict like the location of this another patch, whether it's like in the upper left corner or like on the right, or no, sorry, this upper right corner on the right or on the left or like above or below and so on and so forth. So um and this apparently I don't need any label data where I can just take any images. I can randomly just like take out some patch and then just trying to predict like the location of these patches. So this is one example of p-test task. And these authors here, like, did some evaluation of this like p-test task. They want to know what they actually learn, and then they use clustering to kind of to evaluate the method. So they have this like difference like for uh, either like pre-train the model using ImageNet, or like you have like random initialization. Of course, this will be kind of silly. And then this one will be like using this learning this pre-train using this relative position. Uh, and you see they did pretty well even compared with ImageNet. And interestingly, like for this one, for example, like this guy here, they seems to be more resilient to like color changes. Like it it here like, it's basically doing clustering, right? You're given this input and see like what features is similar to this one. And for if you use this like relative positioning as your pre-training, it's kind of like more uh, I should say like more in indifference like to the color changes. So and this is some other epic example of like um, this p-test task. For example, like I can have like images trying to predict the rotation. So for example, like I have an image, it just rotate with like several different angles. I either like 90 degrees or 180, just flip it completely, or like I flip it to the left, counterclockwise or anti-clockwise. Yeah, counterclockwise or clockwise, and then try to predict like whether it's flip or like it just turn around like clockwise or counterclockwise. And and another example is colorization. We have an image, like we have a color image to start with, and then we just like make it a grayscale image, like black and white, and trying to like take this as an input and predict back the original color. And and yet this is another example. Let's see, this one is okay. Yeah, this one is a more challenging p-test task. It will just like create a jigsaw puzzle. So you start with like maybe like also like 3 by 3 here, but then you move the pieces around. So you maybe you this piece move to here, this piece move to here, and so on and so forth. Then you will try to train the model such that will classify back the permutation. Uh, and here the model like you can do it like a Siamese network. The Siamese network will be basically for each of these patches coming in, you collect to like a network more or less the same weight. Oh, no, I should say more or less same weight. They will be like same weight. The weight will be shared, like identical networks. And then like after you go through these networks like to generate some features, like these features will be matched like to another laterals here, or like maybe just a single layer here showing, and then to do the classification. Um, so this is some example for images. So there's also some example for video. Let's say if I have video sequence, I can also create some p-test tasks like this. Uh, say just have like here, like have like several frames here, three consecutive frames. So what you're trying to predict here is trying to see if like this frame in the middle is indeed an interpolation of like these 2 frames here. Um, and so you can have an input like this, like again use a Siamese network, and then like to decide whether it's a correct or incorrect tuples. So whether like it's a the sequence like, is really this one and then this one or this one, or like it's maybe like extracted by frames extracted from some um, random extracted randomly. And here, this they call it like shuffle and learn. And here they illustrate like what they actually learn like by doing this p-test task. So they try to visualize that like using like again some query, like put into a video and try to see like what's the newest label, like you again do some clustering to see like what sequence of video is like similar to this video here. So it's kind of interesting, like what it learned. For example, like here you see like for image lat and they this one like they kind of if you look at just here, so it's quite good. So of course like the random I can almost ignore it. Like it 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 do quite good in the sense that it seems like, but if you compare the image lat, maybe this one you say okay, this one does not seems to be as similar as this one. So you see like at least the background is kind of different, right? This has some kind of like Asian like architecture here, and this is a concrete road, and this is like all grasses, right? This is all grasses, right? And then background have trees and so on. But what they find is like the interesting thing they learn like in this shuffle and learn is like it seems that they learn the pose of the scene. Uh, of the individual. So you can see like this guy's doing a handstand, like it's also like managed to find like subject is also doing handstand. And these two poses is like comparatively more similar than this one, I would say. Um this is a kind of shuffle and learn. And of course you can be creative but honestly I guess I probably now maybe it's too late. So you uh probably people already think of lots of different combinations already, but it's good to be aware of like this kind of p-test tasks. For example, like if you don't really have label data or like label data is very expensive, then like it's always that you can kind of like see if you can borrow ideas from this kind of research line to see like to create to train your model more effectively. Um, and this is another example like when you have a basically a video sequence, of course like we will have like video stream and also the audio streams, right? So then we can again like just try to train whether it's like these two stream um are close to one another. I should say like coming from the same video. So I can have like this stream is like this audio stream is actually yeah aligned with this video sequence, or maybe I can extract another audio stream that is like independent of this video sequence. And this is a very common, like this is a very common thing like that people do is like you have things that is similar, you try to put it together, or like they should be relevant, you try to train them and see if like you can train the model to know that they're really like close to one another. Or like then you put in something that is not relevant and try to see if you can figure out they are not um, belong to the same um, data point. Okay, so any questions up to now? And oh yeah, okay. This one I'm thinking like what this one is trying to show. So this one trying to test like what is for example, like after we pre-train the model, let's say I pre-train the convlet, so I can pull out, let's say, for example, I can use the last layer to and kind of input this last layer into another like several other little laterals layer to kind of like to and then finally to handle up kind of like a downstream task, right? Or I can also use the earlier layers to do that, or like I can use an even earlier layer. So this is trying to test like if I use different level of this layer, like what's the difference for that? Okay, maybe before I show you here, let me be like, what do you think? Like, uh, so let's say if I have this last layer and the second last layer, so if I pull so this is a question here. Let's say this last layer, I call it an, let's say, and this one is a an minus one. This layer, let's say. So which one you think would be better? Like typically, if I use that to as feature for a p-test task, or sorry, not for a downstream task later on, you will get better result if you're using an-1, or you will get better result with an. So question is clear, I guess. Okay. So others say here, or like they you're pondering. Yeah, you have several like an-1. Yes, actually, you somehow like uh it may be surprising, but maybe not. Like after you think a little bit more, at first you probably will think that an would be better. Like you kind of like have a more refined feature, but it turns out like most of the time, like the earlier layer, the at least the layer like one layer earlier will be better. For example, this one here, it try different layers here. Like in the earlier layers, the if you take it as feature, it's not good. It kind of like increase and improve and improve, and then up to this layer improve like the peak here. But if you use the last layer, etc., there's a drop in performance. Um, so if you think about that, the reason is it's not surprising, because like after all, like this um p-test task and this downstream task is not exactly the same. Here you're doing, for example, this jigsaw puzzle here, but here maybe you are doing classifying like a cat or dog. So there's a chance that like you are kind of like overfitting here. So when in the last layer, you are really extracting features like focus to solve this jigsaw puzzle. So therefore, maybe it's not as useful like to handle some more general tasks. So know that this is an interesting characteristics, but it's not always this case like for self-supervised learning. So as we talk about later on, like some other technique, for example, like uh, using like contrastive learning, oftentimes that you can use even the last layer, you continue to improve like with the um, if you take that as the feature, say each layers will continue to improve, and you can use the last layer. But if you're training using p-test task and then use it like later on for a downstream task, so you want to try like at least also the second last layer to see actually you will get better performance. Um. So and okay. So now okay, I will talk about this technique known as a cluster fit, like by the author. So, so what I did is they use a um just a pre-train a model. So here like they don't really care too much about the p-test task. They basically just there's no p-test task here, you're just doing clustering. So you have let's say have a ladder here. So the ladder is like actually I should say that I shouldn't say that. Like you have this ladder is pre-trained. You can be pre-trained using some p-test task, or like you can pre-train in some other way, or like it can be transfer learning from somewhere else. But it doesn't matter. It's just like some pre-trained network here, and then you think of this pre-trained network like as some form to generate your features. So then you input some images, some data coming in, and then like you like in the previous case here, depending on each individual layer. For example, I can like take the last layer and use that as some kind of features, right? And if I take this as feature, I can do clustering, right? So I would just like have the input put into different clusters here, and then like input like of the same cluster. For example, like this data, like let's say like maybe this like this image, it looks like trees here, put into cluster one here. I'll just have this cluster label as if like some pseudo labels, and I will use these pseudo labels to train another lateral. So now I will have like another network. I use this network. I will just train this network, and and then like after I will use this network instead. So it's like clear is more involved than what we have earlier. So what we have earlier probably is like we have some p-test tasks, and then like given the p-test task, I will just train a network like this one here. But here is like a little bit more, have a little bit more steps. So we pre-train with a different network here, but these different networks basically will be used to generate labels. And the labels will be, of course, like and the labels like will be grouped together like with some clustering algorithm. We can use any clustering algorithm and then group the labels together, and then like we'll use these pseudo labels to train a network instead. So it's clear. By the way, maybe I asked a
It
question. Yes.
it's clear. So what is this called though?
Oh,
This
okay. This called custom fit by the author. Um, but I don't know, like because this kind of like active research area, I don't know whether like
Okay, that's fine. I wanted to know how I could look up more. Thank you.
yeah, yeah. I mean like I have a feeling like probably like someone else introduce a very similar idea, like give it a different name, but like yeah, by because like this author like he gave this like kind of lecture on like self-supervised learning and kind of like more or less promote his own work there, and then he mentioned that this work, but this is kind of interesting as you can see, and maybe as I said like just a participation question. How many of you know distillation? Heard of distillation? So it's not about alcohol. Yeah. So when I yeah. No, it's not chemistry. Like yeah, we learn high school chemistry. I mean, we call that we have some kind of distillation process, like studying chemistry. But here is a different context. Like they in machine learning, people also talk about distillation, and I'm a little bit confused at first. I hopefully I can explain clearly because I that's also like people refer to uh, something similar concept like this like called distillation, like very similar setup to train a model. But in that one, when for if you do something like for example a distillation, will be something like you also pre-train a model, or like you can think of like you have a model, um, you train typically say a supervised model, so you train with like some label, like so here we won't be clustering, so you actually yeah okay I can, but I mean like forget about this cluster here. If for distillation you will be kind of pre-train a model, and you can think of like generate some labels here, right? So you have a labels here, and and know that like if you train a a model somehow, um for example like if I doing like image like classification, I have 1,000 classes. Typically the output like will be first a score like for each of the classes, and then it will go for a softmax way, uh, and then like I will basically have like kind of the probability, something like that. Typically, we will pick the one with the highest probability as the classify um, yeah classify output. But what we are going to do here is like okay, I cannot remove this anyway. So what we are going to do here is like we will again similar to here, we will use this label to train another model. So so basically, I have a model here. You can think of like I'm doing like image like classification. Okay, I train a model to classify something now, classify cats, dogs, and so on. Now, after I train this model here, I'll just like plug in like data like into this model, right? And then like, I will get labels here. But these labels here now, if I also like take this probability into account, I don't do a hard thresholding in the end. I don't only pick the largest probability output. Then I basically have a soft label here, right? Basically, I give any input here. I may have like 80% looks like a cat, and then like 10% looks like a dog, and so on and so forth, right? And I will use this soft label to train another model instead. So I probably will use that like to train the same kind of problem. Like these two problems can be kind of the same, like both of them is just classifier. But when I train the next model, instead of like using the original data, I will use this synthetic data, or you can say think of like uh, whether I should say synthetic labels, but like labels that is like a smooth label, because I in this case I when I put in the data, the original labels, like the original data, I put a dog, it's always give me, or I should say like put an image here, it will always say it's a dog or it's a cat and so on and so forth, right? But from here, like when I put it here to train again, like this label here doesn't necessarily like all cat, all dogs, or all pigs and so on. Uh, it can be a kind of a fraction of cat and some form. You can think, yeah, if you train this with the same model, then you can think of this a little bit untrained, but you can also like train a totally different model. So for example, like you have this model here, but you generate lots of data here, right? Because like this data, for example, like if you have this model now, and then you put in like images now, like typically what's expensive is the label, right? So if like I have already have this p-train ledger that I can generate labels, then I can just plug in like whatever images here. So I can plug in like images doesn't have label in the past. I can put in as many images as I want. Um, yeah, actually for unsupervised, uh, um, you can think of this kind of yeah, I guess this name here, this terminology here, like especially unsupervised, is a little bit what should I say, fuzzy, the name there. So in the past, like people consider unsupervised learning would be just like without label. I guess like it's good not to overthink like this kind of like terminology, because like um um, because they are not precise at right at the beginning. It's unlike some of these other terminology. Let's say self-supervised learning, on the other hand, is like more actually a little bit um, more precise. So you know that you are training with labels and so on. But when you're using saying unsupervised learning, it's just the opposite of supervised learning. Like kind of like uh, referring to the fact that like I'm not using any labels, right? Label data, right? But you can be not using the label data because you're doing clustering, right? The classic clustering, for example, doing PCA and so on, like we didn't use any label data. But or like maybe we just by design do not use any label data. For example, like the original example we mentioned at the beginning, the language model there, like we are kind of doing unsupervised learning as well, because the data is not labeled. But at the same time, you can think of like it's really supervised learning, because like yeah, so it's a little bit fussy, I would say, like this kind of like definition. Um, so but yeah, supervised learning, I think self-supervised learning is very precise. So in this case, self-supervised learning, you can think of like it's a way to do unsupervised learning, or like to do learning without labels, uh, leveraging some uh, idea of like creating like synthetic labels, or like yeah, creating like yeah, synthetic label, I guess it's okay. Yes. So okay, anyway, I hope it's a bit clear the difference between distillation and this like Clusterfit. So for distillation, you you don't do clustering basically. You don't do clustering, but instead like you just use the original model like typically the original model like is like doing like supervised learning, and you use uh, the original set of data and pre-train this model here, and then afterward use this pre-train model to train another model or train or kind of like refine your original model. So and let's see. Uh, so this is basically repeating what we just said, I guess. So in the standard way, if you think of transfer learning, or doing like let's say like the self-supervised learning using p-test tasks, typically we have like a p-train model like this. It can be a p-test task, or like you p-train with like some other model earlier on, and then like um, you can use this model and then adjust a little bit like to use it in some downstream tasks. But for this custom fit here, so as I mentioned, like we first pre-train this model and do a clustering to generate some pseudo labels, and use these pseudo labels to train a new model. So uh, it's kind of like interesting like to see like this have like quite significant gains if you use this custom fit compared with like some of the jigsaw idea we mentioned earlier. So the jigsaw is like more involved kind of self-supervised learning already, and if you use this custom fit actually do a significant improvement here. um and uh okay, yeah, I guess maybe this one is, oh, oh, okay. I probably I didn't save it like last time. Uh, okay. I guess I need to. Uh, oops. That's which one is that? Just wait a sec. Okay. I guess I need to. Um. Okay. I'll mention one more technique like is a contrastive learning, like a very kind of common technique to do self-supervised learning. So the idea is like it's actually we already like explore a little bit like earlier on. The idea is like if we have some data, so for example, earlier we have like uh images, like if we say I have this image here, if I take a patch here, so this patch should have more correlation with a patch in its labeling region, right? So therefore, like I can train some kind of model to learn the difference, like whether like something is like correlated to itself or like it's not correlated to itself. So I can easily kind of create this label here that's positive labels, sorry, positive data, and I can like create like negative data would be like simply take a patch that far away from this patch. So let's say if I have like these two patches, if I come in, get into my model, they should be like saying that they are far away. So on the other hand, if I have these two guys coming in, I want that like they are close to one another. So oh, this is loud. Uh, so this is an example for that one. So for example, if I have videos here, so of course, if they are consecutive frames, they will be correlated, right? So again, we can put into like some kind of Siamese network, like they are they're basically identical, like have share weight here, and then like after you generate some features here, then like it's trying to train a model here, trying to learn like to rank like whether something is close to one another. So so if we give in a, for example, if I put in a pair of that, like let's see, like here, if I put in like three frames, three patches at one time here, so then I consider maybe like this is a which one? Yeah, this one. Let's say this one is the target patch. So we want to see like whether we want to learn whether like this one is closer to this one, uh, or like this one is sorry, I should say this one is closer to this one, or this one is closer to this one. So and we can do something similar like this one, right? So um, uh, yes, I guess um, this figure is a little bit maybe like misleading. I don't think like this always I put in negative here, always like positive here. I mean like always frame close by like this, always frame. Then that's nothing to learn, right? So it should be like randomly put into here, and then to decide whether like this one is closer to this one or this one closer to this one. So wow, and maybe I'll just directly open this one instead of like putting back and forth. Um, so oh, and also like yeah, actually I didn't show this one earlier. So for Clusterfit, like uh, it consistently better than like distillation. And of course, if you just do like p-train using a p-test task, and yeah, I think earlier I don't know the difference, so I have put a remark here. So and so for contrastive learning, let's just go into like some of these figures. Like, so this is like also just like repeating what I mentioned earlier. So I can have like positive, like we can design positive and negative in the sense like, for example, for the same image, for like kind of like patches that's close to the target patch can be the positive, and the patch that's far away can be negative. Or I can also like kind of extracting frames like from different images, or like from different video, or like taking from different images. So and then in this case, like in the same frame like here, in this case would be positive, but let's say this one and this one will be kind of like will be some negative sample like relative to this guy here. Um, and yeah, this is I think yeah, this one basically like they're comparing, with the original p-test p-test task training. So that we mentioned earlier, just like at the beginning, uh, you have this image here. Let's say like this one. Um, we mentioned right at the beginning, right? So you have the image, you do the transform, different kind of transform, and then trying to predict what kind of transform it did, right? So basically, you can modify in many different ways, right? So I can do like different transform, but ultimately what we're doing here is just trying to predict some kind of property of the transform, right? So instead, like they have this work they call it PIRL. I don't know how to pronounce that. It's a p-test invariant representation learning. So they have like the original image, the image like with a transform. Now they trying to train instead of like to predict the transform, the or like the precise parameter of the transform. They just trying to predict um, uh, to make sure this is like close to one another. So I can put in like something is like here, of course, I put in a transform this guy. So this therefore like these two representations should be close to one another. But at the same time, I also can put in some negative sample. Then in that case, I should push these two sides to be far away from one another in that cases. Um, and I'm also like they mentioned one thing is like uh, uh, you can like this is a little bit technical detail in terms of implementation. It's like if you, for example, if you put in the image, and then you put in like the transform image, like every time you try to what should I say? Mm, oh, yeah, maybe I need to get into this detail again. I can't forgot. Um, Oh, okay. Yeah, 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 yeah. Okay, 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 okay. Yeah, yeah, yeah. I see it. So here is a what I'm saying is like okay, yeah, okay. So because when you train it, you want to put lots of negative samples, right? So of course I put in this I, put in this IT here. I want these two to be close to one another, right? So I generate these features. I should train this kind of layer to make sure these are close to one another. But at the same time, I want these guys to be far away from some negative samples, right? So each time I put an image, if I recompute, like I want to make sure this is far away from like lots of different images. So let's say if I also sample another image and then again I compute features and then check if like this guy is the same. So then I have lots of ways of computations, right? Because I really don't need to start from here. What I need to say, I can simply save the features here. So therefore they have this memory bank concept. So you have like the start right at the beginning. If you have lots of images, you just like create a memory bank, basically just like have this picturing model. So or like generate some kind of features here. So let's say like I picturing this now, and then like, I just like generate the features and I store in this memory bank. So then when I train it, I just do not compute this feature again like for this negative sample, but instead like just pull from this memory bank directly. Um, so is that clear? Uh, but I didn't look into detail, but apparently like you need to update this memory bank like every once in a while because this depend on this model here, right? So if you update this model, this is supposed to be changed as well. But um, yeah, this kind of yeah yeah, but this is like really some implementation issues that but when you have like really lots of negative samples, it is actually quite important. So I guess the rest they have here is like just some evaluation. I won't go into that. Like, of course, like they claiming is like better than many, uh, and contrastive learning is like it's an old concept, but at the same time is kind of like getting like back like some popularity recently because of self-supervised learning. So, but as I mentioned, like the key idea is pretty simple. Like you just think of like you don't have the label. Again, like it's good to have just take this one as an example. Right? You don't have the label, but you can say like these two patches are from the same image, therefore they should be close to one another. But this patch is like from another image, this bubble should be far from this one. So then you can just try to train to this two to be close to one another, but this to be far from one another. So that's the key idea. So that's a quick kind of overview of like self-supervised learning. And I don't know, I have 20, 25 minutes. So I guess what I'm going to do, I guess I will start anyway to talk a little bit like RNN. I will see like how far I will go, and then I just so I'll go rather quickly. As I mentioned, um because there are more interesting topics. Like for example, you guys know attention networks. Oh, actually, maybe this is a good kind of like. Of course, I remember that it was one of you at least like talk about attention network in the presentation, right? So how many of you like heard of attention network before? Ah, yeah, actually, you must have like because you attended those presentations. But maybe I should ask like how many of you know like attention networks before the presentation? Yeah, okay, we will talk about that. So um, in the sense that attention network, you can think of like I shouldn't say a replacement, but like many applications that used to be, for example, like NLP, like natural language processing. Just a couple of years ago, like people are so excited with recurrent neural network because it's beating all these old approaches like in NLP, and and then I just 1 2 years later on, like people come up with this attention networks idea, and then again, like, it's beating all this performance in recurrent neural networks. So um so it's still kind of like useful. I'm thinking that maybe I would even have the final homework assignment, like do a simple RNN there. But we probably can use the same data and try to like train that model like using RNN instead. And also maybe like also combine with CNN maybe. So but anyway, let's see. Uh so the idea, maybe I just like go wide at a model so that we can explain. Maybe this one here. So the idea is pretty simple. So this is a vanilla kind of the simplest RNN model. So basically what we have is again, we have some input, I have some output here. Now I have some hidden layer here. So I have some hidden variables. So I have the model here, like FW is like something kind of generic here, but I say I can have this FW is basically just a linear model. So this FW will take uh, the previous hidden variable and also the current input. Oh, sorry, like current input, like as its argument, and then you create something like that way, like a linear model, just this HT multiplied by this matrix, HT multiplied by this matrix, and then I can do some activation. So okay, therefore like my FT is actually I should say like this is my FW. So this is precisely my FW. It's just some linear units with some activation. So and my output will be like just like based on my hidden variable. And you see like I continue to update this, right? So unlike CNN or the neural network we talk about so far, it's all forward modeling, forward only. So everything just moving forward. So there's no feedback. RNN is a model, like a first model here, we consider here that has a feedback. Like we basically fitting also my current state like to the next state, or like you can think of like the previous state is forward to the current state. Um, and so I have an RNN models here, and you think like what's useful for that? Like apparently, like it'll be useful for application that have a time access there, right? So if it's more natural, like for 1D data, or like at least like there's a time element there that you have like the current state is depends on the previous states and so on. No, it's not. Like the activation function that you can put in and like you can put in something else as well. Like you can put like value or anything. Here just I just this kind of like vanilla example here using 10H. Um and and for example, like okay, one application that you can think of, I can do like stock prediction, right? I can just say this is like XN is just my current stock price today, and then like HT minus one is just hidden variables, right? And then like for the given the current stock price, then I update my hidden variables and then predict like the next stock price. Maybe like this would be like XT plus one. So anyway, and then like this YT okay predict like what yeah, or like you can think of this is a maybe a stop price previously. I plug in a stop price on the previous day, and this will predict the stop price for current day, and so on and so forth, like continue to iterate. And of course, you can also do like um as we mentioned at the beginning, the example like doing the character uh, language model. That actually precisely like as you see here, like uh, there's some example like exactly using RNN to try to train a character model like to predict what's the next character. So if you just look at like a phrase, maybe I just this is a x1, this is x2, and so on, right? I come in like more and more characters. Now I'm trying to predict the next character. This will be my YT here. So maybe this is x2, x3, x4, x5, x6, x7, and I'm trying to predict this. This will be like my y7 will be the next character. And then once I predict that, I can put that back into here. Right? My XA can be like my Y7. And then I will have a pretty interesting language model. Like you can just give a phrase at the beginning, it will just predict like what is going on continuously. So right? So if I have like just give you like recurrent neural networks, then it's trying to uh, um, kind of like compute the rest, like compute the rest of the paragraph or a sentence. Um, And okay, how do we train this? So we have a model here. It's actually a little bit more complicated now. Of course, you when we train it, we here like, we also like still focus on a supervised learning kind of training model here. So to train that, I should know like what's my expected YT here. So if I have a if, for example, I take the language model again, like if I train it with this language model, it's like pretty nice in this sense that like of course I know the YT because it's the next character, right? So I know exactly what is that. So I can do supervised learning for that. Um, so but everything I would say like is very similar to like all the neural network we learned so far. But the only thing be careful is that like I have share weight here, right? Because I have this YH and YXH will be the same like overall right, for each time periods. They are basically the same matrix here. So therefore like they should be updating the same um they basically share weight in the sense I want to say. So uh trading okay um I s- I mean like usually like we'll train this model like using like this propagation full time. So what I mean is simply if I'm kind of like giving some input, like expecting some output, I'm just like unfold the whole model, right? So I have here, like for example, I have a character sequence here, maybe like A, B, C, and so on. I just like spelling like kind of like alphabetically. So I have A, B, C, and so on. And then like here, I predict like this should be B, right? I predict this should be C, and predict this should be D, and so on, right? Now I can again just do backpropagation. Maybe like at the beginning, I don't get this B. Maybe I have a, of course, like this final one. I can have a score. Like for example, if I do a character model, maybe I have 26 character here. So then I have like possible like 26 different outputs. Um, and I will have go for a soft max, and then again maybe I have a distribution that may not be highest with a B. So but anyway, like I can compute the cost, like the loss here, like the difference between this guy to just using like as usual like cost entropy loss. So and my total loss therefore will be the loss like sum over like each of these characters here, right? So maybe this one actually estimate I have the peak here, it's like D here, I have another peak here, right? It's E here. It's okay, but I will compute the loss of this distribution compared with this guy here. So, uh, and then like with this loss, I can compute the gradient, right? So I will compute the gradient with respect to this WH and WX here, and 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 I can backpop that. So actually, I should more like write the total loss here. Uh, should go through this. We should sum all together into like compute some loss here, right? So I have this loss can backpropagate back basically the gradient of the loss backpropagate back, and then I will update like each of the ways here. So I'm this way should be shared ways. So I have an update here, but also we have update here at the same time. I don't know. I should say at the same time, but like, um, yeah, same time is okay, I guess. Not exactly in actual implementation, of course. So, um, yeah, and that's basically it. A little bit remark here. Uh, if you have like the recurrent network here, uh, the initialization, like of course in the past we have initialized the weight only. Think of like initialize the weight, but um, I can also like uh, do a different like, or maybe this one is more interesting. Maybe consider this one. So for example, like I try to train a model. So for example, I train this model here to get into this character, something like that. Right? I have this eventually, what should I say? Um, yeah, this is not yeah, this probably nice. I shouldn't use a character model here, but don't think of this as a character model, but think of like um I this is the time axis here. This is the time axis. So I have the expected output. Like for example, like I want the output here to be something here. Um, and I can I can like both just like force at exactly period time here to have the output is equal to the expected output, or like I can force like uh not just at time t, the output is say to be the same as the desired output, but I also can force maybe t plus one time step. Also, the output is say the same as the desired output, and also t plus two step, and so on. So, um, doing that, like sometimes we will have like some nice behavior, kind of in terms of robustness, because it will be um kind of like you have the solution kind of decaying. Like in the sense, if you just force this guy equal to this one here, you may have like a output that somehow is oscillating. For example, like at this point, like it's equal to this guy, but in the next time step, maybe it's just jump back and equal to something else, and the next time step is equal to something else. But if you force a for consecutive time step is equal to something that um, it sometimes will be beneficial. Uh, so this is a toy example that you see like for another application will be useful using RNN. It's like, for example, if you do simple like calculation, let's say, for example, like I want to train a model to just do addition. So of course, I can train a neural network. Let's say I have, for example, like this here is like 8 digits here, 8 digits here. I can train the networks to do the sum like with 8 digits at 8 digits. But this won't be very flexible because then if I want to change my input to 10 digits and 10 digits, I need to just do it again, right? But here, what I can do is like, instead of like trying to train the model to take the entire one as an input, but I can train it like to take one digit at a time, right? So my model can be like just take the first digit, first two digits and output like one digit here, and then I take the second digits and output the next digit here, and so on and so forth. Then you can train a model like this, and then you can do addition for like arbitrary length of numbers. So okay. So I guess I'll skip this. This is just saying like training RNN is challenging. This is of course because if you do backpropagation full time, then you can think of like the RNN is really a lateral of many layers. So it's like it's always like if your lateral has more layers, it's more difficult to train. Um, and so this is like the same thing here. So okay, I will. Well, okay, I guess I do pretty quickly. Maybe we can or start a new topic next time. Like not even talk about RNN, but we'll see about that. So um, so we talk about this vanilla RNN. Um, a very important like modification is so-called like long short-term memory. I'm sure that you guys heard of that. Uh, and it's basically like okay, this is a rough idea like by Hinton. So it is it's thinking like okay, this is not an uh, exact exact implementation, but this is just a high level concept. You can think of like what LSTM does is like instead of like just trying to um have the input like remember we basically train some hidden function here that take my previous hidden value like ht minus one and my current t step here and output my next time step hidden variable. Um, so for this one, like it's it's difficult to train a model that is going to be able to remember this hidden variable like for a long period of time. For example, like I have like H0 at the beginning, but as I continue to update it, like maybe after 10 steps, like after H10 is like more or less I have no memory of H0 at all. So therefore, like the classic RNN tends to be have like really short memory. That's why we have this modification. Long short-term memory is like saying that I want to have a longer short-term memory. So what it does is like you can think of like it modify the model a little bit to create some kind of gates that this gate can be open, turn on and off to kind of remember whether like something or like don't remember something. For example, like if I have like some of this read gate is on, I'm going to read the input here. And if I have this white gate is on, I'm going to write the output into my memory. If my white gate is not on, then I will just keep my previous memory. Basically, it's not going to change that. And maybe like I also have some keep gate to decide whether I want to forget about my previous memory. So doing that, like you can memorize longer. So this is the original RNN, this is the LSTM. So this is more or less a not precisely as I mentioned as the previous figure, but this is precisely how what is implemented. But you see, like they have like different gates here. Like you have the input gates is like input gates is on. Then each of them, if you look at this, like, each of them is basically you are having very similar to this RNN, right? But instead, like directly output this H here, you could first like generate some of this gate here. Some of this gate is quite easy to understand. So for some this input, like generate the input, um, and I have this. Let's see. Always I generate the output here. So if the O is not on, for example, if this is a sigmoid here, it will be like either 0 or 1, right? Or I should say is close to, yeah, maybe sigmoid say that, right? It's either you saturate, there will be more or less almost 1, or like it will be like almost 0 here. So if O is on, then like you actually get this content updated into your memory here, right? So, but if O is off, that you will be not uh, you basically ignore this guy, right? You output 0. So, and I have F here. It's like that forget gate that you can think of like this. If F is like on, then you remember like what's the previous memory, right? If F is off, then it's not going to memorize that. So anyway, like it's hard to interpret all of this, but to be honest, like most people don't care about this because like they use this LSTM block just as the RNN block, right? Because you look at this thing here, the input is like just a uh uh wait a sec. Yeah, actually the input is basically just like the for example, like if you have like multi-layer of like kind of RNN here, for each of the layer, you have, for example, like for this guy here, you take input from the previous time step of the same layer. I'm also take input like of the same time step of the previous layer, and then I generate output like for the for the next time step also like from for the next okay, sorry, for the next time step and for the upper layer, right? So, and for the LSTM block, you see that it's exactly doing the same thing, right? I have input that I'm taking here and here, then I generate output. I will just pass to like here and here. So I can essentially just forget about like what's inside. Just think of it as a black box and just replace this RNN block with the LSTM block. And oftentimes you will get better performance basically. And besides this, like this is like trying to explain more of this, like, but I won't try to do that even. But um, a remark here, for example, like Andrew Karpathy, like several years ago, he also tried to explain this. Like, his argument is that like if you split out like some of this stuff here, you can see that some of the path here um, uh, you are actually again similar to Westlet. Actually, like what he want to argue is like it's similar to Westlet that like you have sometimes that you have the input will directly go through to the output. So therefore, like in terms of training, you have this skip connection. It's like you have this skip connection that allow you to train better. So this is his argument. So anyway, so this is like just an illustration again. So there's some variation of LSTM, like another very famous one is the GLU. Um, and you can just try that. Like I think like for PyTorch, TensorFlow, they have all this implementation. Basically, you can replace any block that, for example, like using RNN like replaced by a block like with LSTM and GLU. And there's also like many other variations and so on. Yeah, I guess like this is a good time to stop. So I will. Oh, okay, yeah. Remember that this midterm like next Tuesday, and I'll open the connection anyway. So, but you guys don't need to really log in. But I'll open the connection in case there are any questions, and I will have the questions available on Canvas like by the what not three. I'm sorry, like the class start with 4:30, right? Start 4:30, and then like I will let it open until 6 or something. So please allow sometimes for you to scan and upload your solution. So any questions for that? So if not, I guess I will just stop here. So good luck for your midterm. So
Thank you, Professor.
yes.